Okay. So now let's start with the McCulloch-Pitts neuron model. McCulloch-Pitts neuron model. So this McCulloch-Pitts neuron was the earliest network discovered in 1943. So if you see, it was discovered in 1943, and it is called usually called as what MP neuron. So if in the exam it is asked that designed this network with MP neuron. So MP neuron or McCulloch-Pitts neuron, it's the same thing. So Pitts ka P is there and McCulloch ka M is there. So that's why this is called the MP neuron. So MP neuron are connected by directed weighted graphs. So it's very simple circuit. Like one node will be there and the other inputs will be connected to that particular node with the different weights, right? And some kind of activation function will be there for that particular node. The way we solve the yesterday's problem exactly in the similar way, McCulloch-Pitts neuron model will be there. Only thing which function you will going to select. So most of the time it will be binary sigmoid function where we'll be having the output in the form of 0 or 1. So the weights associated with the communication link may be excitatory weights or positive weights or the negative weights. So both the kind of signal can be there. Either it will be excitatory signal. If the excitatory signal is there, it will be positive weights like +1. If inhibitory signal is there, then the weights will be negative. Then all the excitatory weights entering into a particular neuron will have the same weight. So this is one thing. Then the threshold plays a very important role in MP neuron. So there is a fixed threshold for each neuron, and if the net input to the neuron is greater than the threshold, then the neuron will fire. So this is a basic criteria. The total net input will be collected, and if it will increase, if it will surpass the threshold value, then the neuron will going to fire. Otherwise, it will not fire. So this is a basic diagram. So for example, if we see here, this is a neuron where we are having one kind of function, okay, where we have written W transpose into X. This is one function. And for calculating total net inputs, the formula we know X1 into W1 plus X2 into W2 like this. We will do the summation. We will calculate next, net input, and then we will substitute inside the function. And depending on that, we will try to get the output. Okay. So the neuron output signal is given as output is equal to f of W transpose into X, or f is equal to sigma I from 1 to n, and we will do multiplication with all the weights and inputs and plus their summation. So W1 X1 plus W2 X2 like this. So here where W is what? Weight matrix, and it's given by W1, W2, W3, Wn transpose of that. And X is what? An input vector where X can be written as X1, X2 up to Xn till a transpose of that. So the net input is calculated by this particular formula. Net is equal to W transpose into X. So this will give us the net input, and W is equal to 1 for excitatory synapses, and W is equal to -1 for inhibitory synapses. Okay, now this is important point. So although this is very simplistic, it has substantial computing potential. Okay, it can perform basic logic operations. So it can perform basic logic operation like NOT, OR, and. So we will basically try to design these all gates with the help of this McCulloch-Pitts neuron model, right? It can perform certain basic operation like NOT, OR, and AND, provided its weights and thresholds are appropriately selected. So we will have to select proper threshold and weights, and so that our output should be proper in that fashion. I mean, if not, we are selecting or we are selecting, so we have to check the output. According to that, we should get the output in such a way that we have to select the input and weights. We have to adjust the weights in that way. Then multivariable combinational function can be implemented using either NOT or alternatively the NOT and AND Boolean operation. So even multivariable combination function can also be implemented with the inclusion of NOT and OR, right? And NOT and AND. But this model has no learning capability. Okay, it cannot learn it. So this model cannot solve XOR problem and XNOR problem. So XOR or XNOR cannot be implemented. If you want to implement it, then some addition we'll have to do in that particular stuff. So this is the problem. Now, before solving this, there is one concept that is called as linear separability. So let's see that one first. Linear separability. So let's say so this is x1, x2, and this is output. So 0, 0, 0, 1, 1, 0, 1, 1. So let's say suppose this is AND operation. So we'll get 0, 0, 0, and 1. Okay. Now let's plot this. So here we will take x1 and this we will take as x2. This will be the origin, let's say. Now what we will do, the first pair is what? It's 0, 0. Okay. The first one is 0, 0 and output will be what? 0, 0. So x1 is 0 and this one is 0. And what output we are getting? We are getting output 0. So for a 0 class, so if we see this particular column, output column, we are having two different classes of output. One class is 0 and another class is what? 1. Okay, so there are two classes, two different classes. So the 0 class I'll represent by 0 like this. So here 1 point I got. Then next point, let's see, the x1 is 0 but x2 is 1. So this point, and this is again 0. Then the next point is what? 1 comma 0. So let's say 1 is over here and 0 is 1 is over here and 0 is this one. So I mean this point only, and this is what? 0. Then the next point is 1, 1. So 1, 1 will be somewhere. This is 1 and this is 1. So this point and this point is what? 1. It's a separate class. So this point we will mark as what? Cross, let's say. So two different classes are there, 0 class and this cross class. And if we are able to separate these both the classes with a single decision line, single straight decision line, then this problem can be called as what? Linear separable problem. So for example, we can separate this by a single straight line like this, and this line is called as a decision boundary. Decision boundary, right? This line is called a decision boundary. So remember one thing, we should not draw like this. Okay, we should not draw a curve like this. Only a straight line should be there and should be able to separate properly all the classes, right? So if there are two classes, the decision boundary should be able to separate both the classes. And if this is happening, then this problem is called as a linear separable problem, right? Let's take one more example. So for example, here x1, x2.
So can you just repeat, sir, 1 second? So
Which one? Which one?
so the previous one, sir. Can you just repeat 1 second?
Okay, okay. So best let me take one example. Let's take OR example. Okay. So now let's see the graph of OR. So we are having input 0, 0, 0, 1, 1, 0, and 1, 1. So for this one, we'll get output 0. For this one, 1, 1, and 1. Now two different classes are there. One class is 0 class and another class is 1 class. Okay. So this one signal, we say that this is the excitatory signal. This is a firing condition, and this is what inhibitory condition. Okay. If we will get this particular output, the neuron will not fire. So that I will explain later. But let's assume that here there are two different classes. One is 0 class and another is 1 class. Now we will going to plot this. So let's plot it. Okay. So this is my x1. This is my x2. So the first input is what? First input x1, x2. First input 0, 0 and the output is 0. So this 0, 0 will come over here. 0, 1. 0, 1. So and output is what? 1. So I'll mark over here as cross. Then 1, 0, 1, 0. So this is 1. 1, 1, 1. So this is 1. 1, 1, 1. Right? Now whether I am able to separate these both the classes, okay, there were two classes, whether I am able to separate, whether I am able to separate both the classes by one straight line. So I'll just draw over here one straight line like this. And yes, I am able to separate both the classes by one single straight line. Hence, this problem is what? Linear separable problem. Okay, linear separable problem. So remember this concept, the linear separable problem. Right. Now let's take one more example. XOR x1, x2, output 0 0 0 1 1 0 1 1. Okay, so this will be 0 1 1 0, right? So for dissimilar inputs you will get one output, for similar inputs you will get 0. So this is XOR. Let's plot it. X1 x2 0 0 0 0 1 0 1 1 1 0 1, then 1 1 0. Now let's try to separate it with one single line. So let's say I'm drawing like this. So this will not separate all, I mean both the classes with one line. I cannot draw two lines, okay, like this. So I'm not able to separate it. This is 0 1 and 0 over here. So I don't have, I mean any, I cannot draw like curve like this. So this is not a linear separable problem. So XOR is not a linear separable problem. Clear all of you? Any doubt in this? If you have any doubt till here, please ask me. Okay. So let's start. Write the question. Implement AND function using McCulloch-Pitts neuron. Take binary data. Take binary data. Implement AND function using McCulloch-Pitts neuron. Take binary data. Okay. So there are two different methods to solve this particular problem. All of you can hear me?
Yes, sir. Yes, sir.
Yes,
Okay.
sir. Yes.
So there are two different methods. So let's first focus on this particular method. Okay, then we will see the second one. Second one is by trial and error method. So first we'll solve step by step properly, and it's up to you. You can solve by any method, whichever method is suitable for you. Right? I find that the first method is more suitable for all the students. Second method requires some kind of thinking, right, and guessing. So you just first try by the first method. I'll solve by both the methods. So it's up to you. Okay, so to solve this particular problem and problem, we will, the first step will be what? We will draw the table. So first we will make the table. Then after making the table, we will take x1 x2 and y output. So if you see the table for and for 1 1 condition, we will get output as 1, and this we will mark as a firing condition. So if the output is 1, we will say this is a excitatory signal and it's a firing condition. But for rest of the signals, for 1 0 0 1 and 0 0, we are getting 0 output. So this we will call as what? Inhibitory signals. Okay, where inhibition occurs. So if these are the outputs, the neuron will not going to fire. But if this is a condition, the output is 1, then the neuron will going to fire. So the first step will be always to draw the table. The second step is what? Draw the diagram of that one, that figure. So to show that whether this is a linear separable or not. So you can make the diagram and then check whether it's a linear separable or not. If it's linear separable, you can just write this problem is linear separable. So make the graph of and after making the graph of and, you can see over here that three classes are there, 0 0 0. So three classes are 0 0 0. Only one class is there, that is 1 1, this one, which is coming over here. So if you try to draw one straight line, then the class this one class can be easily separated by the 0 class. So I hope this you understood how to check whether this is a linear separable problem or not. So this is the second step. Now this problem is linear separable problem, so we can easily solve by McCulloch-Pitts model. Okay, now the third step will be draw the circuit of that. So circuit of this one, it's a linear separable problem. It's very simple. We will require one neuron and two inputs. For two inputs, x1 and x2, we will require that one. And weights, so w1 w2, don't mark this one as 1 1. So let's say w1 and w2 by weights, x1 and x2 are connected to this y, okay, neuron. And here we will be collecting y in total net input, and then we will try to get the output from this one. So this will be the basic circuit. What we have to determine, we have to determine that what should be the weight w1 and w2. Now what we will do, we will run the first case where we will assume. So we have to assume and we have to then solve the problem if we are getting properly. So if we are getting proper answer, then we can say that the assumed weight was right. So for example, in the first case we have assumed, that's why in the diagram is shown what w1 is equal to 1, w2 equal to 1. So you can write like this. Let's say the case 1 is assume both weights are w1 is equal to w2 is equal to 1. So we have assumed that both the weights are 1, and then we will try to solve the problem. Now on what basis we will try to solve the problem? We will use the formula, that is y in is equal to w1 x1 plus w2 x2. See how we will calculate the total net input at this particular node. We will calculate the total net input at this particular weight by multiplying this input into this weight plus this input into weight. Okay, and the summation of both will give us total net input at this particular node. So this is the same formula. Y is equal to w1 x1 plus w2 x2. So this is my formula. Now we got the formula and we have the inputs, right? We have the inputs and we have assumed the weights also. So we will try to find out the y in from all these four patterns. Okay, we will going to find out the y in for all these four patterns first. So let's try to calculate. So we will take the first pattern. The first pattern is 1 1, second pattern 1 0, third pattern 0 1, and the fourth pattern 0 0. So let's take the first pattern, that is 1 1. So for 1 1 we will going to solve like this. Y in is equal to so we will substitute over here. W1 is what? If you see here, we have assumed w1 w2 equal to 1. So w1 1 into x1 is also 1, right? Because the first pattern is what? 1 1. So both x1 and x2 are 1. So that means 1 into 1 plus 1 into 1, right? So that means y in will be what? 1 plus 1 2. So that's why the total y in is what? 2 for 1 1 pattern. Okay, is there any doubt? We have to simply substitute this value inside this particular formula and calculate the y. So for 1 0, for example, for 1 0, so x1 is 1 and w1 and w2 are 1 1 only. So 1 into 1, this will be 1 plus w2 is 0. So 0 into x2 is 1. So this will become 0. So the y in will be what? 1. Then for 0 1, 0 1 first part will become 0. This will be 1. So y in will be equal to 1. For 0 0 both will become 0. So y in will be equal to 0. Now once you got this y in, now it's our responsibility, our job is to check, to match whether this associates with this particular output or not. So that means in the table what we saw, for the first pair it should fire, and for other rest of the cases there should be what? Inhibition. In the similar fashion, whether we are getting the relation over here also or not. So we can choose the threshold. That's a freedom we are having. We can choose the threshold, but after choosing the threshold, whether for the first condition, whether this particular condition, the first one, we are able to separate with the rest one or not. So that we have to check. So after calculation of y, we found that for the first case, the output is 2, but for the rest of the cases, it's 110. Now, if we will apply the threshold, let's say if the output is greater than 1, input is greater than 1, then the output will be 1. Less than equal to 1 will be 0. So in that way, we can separate it out. Or we can also take the threshold as what 2, and we can say that if the output is input is total y in is greater than equal to 2, then the output is what? 1. Less than 2, the output will be 0. So if we will take these two threshold condition, then we are seeing that we can easily separate out the first condition, that is the excitatory condition according to our table, the first one, with the rest of the condition, where rest of the cases are what? For inhibition, right? So that means whatever weights we have assumed over above in the first case, weights were right. Okay, those weights were right. If we are not getting proper condition, if we are not able to separate it out properly, that means assumed weight was not right, and then we'll have to change, modify the weights, and then we will again have to calculate. But here we saw that after assuming the first weight w1 w2 equal to 1, the first case easily we can separate it out from rest of the cases. So so that means for the assumed weight is right, and then we can select, okay, the same thing, and we can write this particular equation. We can write in this particular format that from the calculated net inputs, see that if it's possible to fire the neuron for the input 1 1. If yes, then weights are suitable. Here it's possible, so fix the threshold. So we will fix the threshold that theta is greater than equal to 2. So if we will decide like this, that y is equal to, that means the output will be what? Output will be equal to, so whatever net input we'll be getting, that we will going to substitute inside some function, right? So that's what, this is the notation. We are substituting that y in inside a function, and the function output will be what? 1 if y in is greater than equal to 2. So theta we have decided as 2 threshold. So and if the y in is less than 2, then we are saying it's 0. So based on this particular condition, okay, we are seeing that we can easily separate it out, the first case with the rest of the cases, and this is what we have designed the circuit with this particular model. So in this, if you are having any doubt, please ask me, and just try to solve this particular problem the way I explained, by yourself only, by this method, and then you will understand whether you are having any doubt or not. And if you have any doubt, please ask me.
Sir, can you re-explain the second half, sir? This
Okay,
part which you
yeah,
just finished right now.
definitely,
The second
definitely.
method, the
Second method, okay, okay.
this
But
part.
first focus on the first method, and I want that you should also solve the or wala problem with the first method
Okay,
only.
okay, sir.
Then I will explain the second method.
Okay, sir.
Yeah.
Sir, please explain that net input wala part.
Okay. So I'll solve along with you over here. Okay. Let's see from the start. So suppose I have given and and problem. So my first job is what? First step is what? To draw the table. So x1, x2, and the output. So this is 1 1, this output is 1 0 1 0 1 0 0, and then the next one is 0 0 0. Okay, so if you see here, this particular condition, we can say this is what? Excitatory signal, excitatory, and these three inhibitory, right? So the first case is different with the other cases. So there are only two cases. First one is excitatory, second is inhibitory. Now what we will going to do, we will just going to draw the graph to check whether it's a linear separable problem or not. So let's draw the graph x1 and x2. Now if you try to solve this particular problem, the first one is x1 x1, so here we will get one cross, okay, and rest, and the second case, let's say 0 1, so 0, okay, 0 1, so that means what, here we will get 1 0. Next is what, 1 0, so 1 0, right? So this will be one case, and then 0 0, so there will be one case over here. Now this problem we can separate it by one single line. So this is decision boundary. So by the decision boundary or decision line, we can easily separate both the classes. So this is what, a linear, hence it is a linear separable problem. Hence it's linearly separable. Okay, linearly separable. So you must write this statement. After this, the next point is what, we will draw the circuit. So let's say, suppose this input, this neuron I have selected, and these two are the inputs. I know that x1 and x2 are the inputs. So x1 x2, I am assuming that they are connected with weights w1 and w2, and here the net input which will come, I am saying y in, and the output which will come, I am saying it's y. Okay, so I will make the formula for y in. Y in will be equal to x1 w1 x2 w2. Okay, so one formula we have made. Now let's assume the first case, case 1, we will assume w1 is equal to w2 is equal to 1. So let's assume this one, and then try to solve this particular problem. So what we will do, for every pair of I mean these, okay, these inputs, we will going to calculate what is the y, right? So first we will check first one with the first pair, that is 1 1. Okay, 1 1. So here we know that the x, okay, for this particular pair, can you tell me the x1 is 1, right? And for x2 is what, that is also 1, and w1 and w2 we have already assumed what, 1. So for this particular pair, y in will be equal to what, let's substitute inside this. So x1 is 1 into 1 plus x2 is 1 into w2 is 1, so this will be 2, right? So for the first pair, y in is what, 2. Now let's calculate for the second one. The second is, let's say 0 1. So for 0 1, what will be the y in? So if this is 0 multiplied by something, right, this will become 0. I mean the first part will become 0. The next part is what, x2 into w2. x2 is 1 and w2 is also 1. So this will become, this will become 1. And then the third is what, 1 0. So y in will be what, for 1 0. So the second part will become 0, but the first part will be 1. So y in will be 1. Then next is 0 0. For 0 0 0 0, we will get y in as what, 0, right? Now what we have to see, we got the 4 output. Now we have to see according to table, in the first case we got the firing condition, that is the excitatory signal for the first case, that is for the pair 1 1, and for rest of the 3 cases we are getting inhibitory. So from our calculation, we have to check if we will going to select certain threshold value theta, okay, then whether we are able to separate this particular first case with the rest of the cases or not. So this is our task. Now what threshold we must choose so that we can easily separate out these 3 cases with this particular, and output should be only 1 and 0. Okay, output should be 1 and 0. So if I select the theta as what, 2, let's say, right, and I'm saying that if y in is greater than equal to 2, then only you must produce the output as 1. if y is less than 2, then the output should be 0. Then if we check it here, the y is what, 2. So for this one, I will get the output as 1. Here y is 1, which is less than 2, output 0. Here y is what, 1. So it is less than 2, output 0. This one is output also 0. So if we see here, we are easily getting the output 1, that is excitatory signal for the first pair, this one. And for the rest of the conditions, we are easily getting what, we are getting 0. So that means whatever weights we assumed 1 1, okay, here 1 1, that was right. And then we can finally consider this as the final thing. And you can write over here, hence the for the firing condition, you can say that after selecting the theta as what, 2, threshold as 2, we are getting the firing condition. Okay, we can easily separate out the firing class with the other inhibitory classes. So whatever weights we assume, that is right. And then finally you can draw this particular circuit where you can show W1 equal to 1, W2 equal to 1, and this is what, X1, X2, and here you can get the output y. This will be y in, and you can write the equation y output will be equal to f of y in, right? So this we will get the output when we will going to substitute the total net input inside the function, and this will produce 1 or 0, 1 or 0. So when we will get 1, when our theta is what, when y in we are choosing at greater than equal to 2, and when y in less than 2. Either you take theta or y in. If you write over here y in only, then also it's right. Okay, so theta or y in both are same. So you can write over here. Here also, if you present theta greater than equal to 2 or theta less than 2, that's okay. So best represent by y in only, and this will be our final design. Any doubt in this till here, all of you?
No.
Oh. Now what I want, on the similar fashion, you just try to solve the second problem also. That is here I am giving the OR problem. OR problem.
Sir, can you just show your notes before doing this? We could just write that. We just come.
Okay, okay.
So do we need to write the second method?
No, don't write second method. I'll explain, then you write. Okay. Don't
Okay.
concentrate on the second method right now because it will confuse all of you. So don't concentrate on the second method. Just first do the first method and just concentrate on the first method. And if you're finding it easy, then obviously you don't see also the second method. Okay. But I will explain. But if you are, this is first one is more easy, so you can go with the first one.
Yes, sir. Okay,
Yeah.
sir.
Sir, could you just scroll down a bit?
Yeah. If anything you are not understanding, please let me know. This is assume both the weights W1 equal to W2 equal to 1. Then for four inputs, calculate the net input, that is Y in is equal to W1 X1 plus W2 X2. And for all the four cases, you can calculate Y in. So this is a OR function, and it's given that implement OR function use binary data only. So first method is what, with the first method we are solving this, and we will first draw the table. So this is x1, x2, and this is output. If we try to make this particular table 1 1 0 1 1 0 0 0, so with the first three cases you will find that there is a firing class, okay, firing condition, and with the last one we are getting the inhibition, right, inhibitory condition. So we will try to make the circuit and try to assume certain weight, and we will try to find out whether this will hold true or not. Okay. So the diagram graph to check out whether this is linearly separable or not. And what we are seeing that after plotting this particular graph, we can easily separate it out both the classes by a single straight line. So that means this problem is what, a linearly separable problem. And then after that we can calculate the total net input. So first case we are assuming that W1 is equal to W2 is equal to 1, and this is the formula Y in is equal to W1 x1 plus W2 x2 to calculate the total net input. So for the first pattern, that is 1 1, we are calculating, and we will get what, 2. For 0 1 we will calculate, so the first will become 0, we will get 1. For 1 0, second part will become 0, so we will get output input 1. For the last case we will get input at was 0. Now again we got 2 1 1 0. Now whether it's possible to select any threshold value, and whether it's possible to separate it out the last case with the rest of the three cases or not, this is what we have to find out. Because if we see the table, the first three cases is the firing condition, and the last condition is what, inhibitory condition. We have to find out certain threshold value by which, after choosing there, we should be able to separate it out the first three cases with the last case. So if we will going to select the threshold value as 1, so if I'll say that when y in is then equal to 1, then the output will be 1, otherwise the output will be 0. So if I'll select 1 as a threshold value, then I can easily separate out all the three cases with the last one, right? And this is what, so that means the assumed weights were right, and we have implemented this. So you can write this particular thing, y equal to 1 0, y is greater than equal to 1, then the output will be 1, otherwise output will be 0. And this also you must mention w1 w2 equal to 1 for this problem, and theta or y in is equal to 1. And circuit also, you draw here circuit, I have not drawn, so you can also draw the circuit and you can represent all these values. Okay, so you can draw the circuit. Okay, whether you understood this or
Yes, sir.
okay. Now let's try to understand by the second method. I don't want anybody to get confused. You can remember the first method, but I will also explain with the second method. Let's see. We're going to solve the first problem, that is the AND problem, with the help of second method. Now the first two steps will remain the same. Like, we have to first make the table, and we have to find out which one is the firing condition and which one is what, the inhibitory condition. And then after that, draw the graph. So for the graph, you can find out that this problem is a linearly separable problem, because we can easily separate out both the classes too with a one single boundary. Then after that, we have to write the logic. Okay, the logic for firing and logic for inhibitory condition. So this logic you can write in a positive logic or negative logic. For example, both the logic is correct. For example, suppose I am writing like this: W1 into x1 plus W2 into x2 should be greater than theta for firing condition, and then the inhibitory condition can be easily set as what, less than equal to theta. So I can write W1 x1 plus W2 x2 should be less than equal to theta for inhibition. And for firing condition, it should be W1 x1 plus W2 x2 should be greater than equal to theta, and this should be less than equal to theta. Or let's say you can also say W1 x1 plus W2 x2 should be less than theta, then it's a firing, and greater than equal to theta, then inhibition. So it's up to you what logic you are deciding. So let's say, suppose we are deciding this particular logic, the firing condition, inhibitory condition, simple logic, W1 x1 plus W2 x2 should be greater than theta, then we will say this is a firing condition. And for W1 x1 plus W2 x2 should be less than equal to theta for inhibitory condition. So this simple logic we have applied. Now we will going to test it. Okay, we will going to check it. So first of all we will assume the weights, and weights we assume what, W1 is equal to W2 equal to 1, right? So once we will assume the weights, we will just going to substitute in this particular formula for all the cases. So for the first case is what, the 1 1. So we'll just substitute in this particular formula. So we will be having what, W1 into 1, right? So 1 into 1 plus 1 into 1 is greater than theta. Clear? So that means what? We will substitute the input first. Let's say first we will substitute the inputs. So x1 and x2 is 1 1, and we will substitute, we will get this equation, W1 plus W2 is greater than theta. So we have to basically make the equation first. Then the next pair is what? And next pair is for inhibition, right? So firing is over. For firing we got this particular equation. Now the inhibition is there. So for inhibition we got this particular equation. So now this pair we will substitute in this equation. So x1 is 0, so this part will become 0, and x2 is 1. So that means W2, okay, x2 is 1. So W2 is less than equal to theta. So second equation will become W2 less than equal to theta. Now the third is what, 1 comma 0. So for 1 0, again this is inhibitory condition, so we will going to substitute in this particular equation. So 1, that is x1 is 1, so W1 plus x2 is 0, so this will become 0. So W1 is less than equal to theta. This will become the next equation. And the last equation where both the inputs are 0, so that means both the values are 0. So 0 is less than equal to theta. This will become the fourth equation. Now from all these four equations, we have to assume the W1, W2 and theta value in such a way that all the four conditions must satisfy. And then if all the four conditions are getting satisfied, that means the chosen value is perfect. So for example, if we will choose W1, W2 equal to 1 and theta equal to 1, let's verify. So if W1 and W2 is 1, so 1 plus 1, 2, 2 is greater than theta is 1. Yeah, the first condition is true. Only W2 is less than equal to theta, so W2 is 1, theta is 1. Okay, 1 is less than equal to 1 is greater than equal to 1. That is also correct. Then W1 is less than equal to theta. So W1 is 1, theta is 1. This is also verified. Then whether theta is greater than equal to 0. Okay, so theta is 1, it's greater than 0. So all the conditions are getting satisfied. So the chosen weights and the theta is proper, and then we can draw the circuit because it's satisfying all the four conditions. And we can draw the circuit like this: W1 equal to 1, W2 equal to 1, theta equal to 1. And at the end, we can write the equation. So whatever the firing equation we are having, greater than theta. So here we have written theta greater than 1, 1 output, theta less than equal to 1, output will be 0. So this is our second method, where we have to first make the equation for firing and inhibition, and then after that simply substitute all the pairs value and make the four equation. And after making the equation, just you will have to do the trial and error, and from your side only you will have to select the weights value and theta value, and then you need to verify. It can be any set of values, okay, need not be the same. You can get any other set of values also, and your answer can be correct. Only thing, you need to verify whether it's validating all the four equation or not. So this is the second method. Is there any doubt in this? If you're not understood anything, please ask me in the second method. Now it's up to you. Both the methods are there. You can follow any particular always, because I don't know if they will going to give you some equation like a problem can be of this particular form, that there is a two condition, one is a firing and this is inhibition condition, and then choose the proper proper weight and theta. Okay, so they can give you one problem in this particular format. So if you don't know this particular method, then you won't be able to solve that problem. That's why I also explain this particular method.
Sir, can you scroll down a little bit?
Okay.
Yes, sir.
So by second method, you can solve now OR problem also. OR problem. So for OR, you can select this particular logic. If we see for the first three cases, we are getting 1, and for the last cases, that is inhibitory condition. For excitatory condition, you can make this particular logic: W1 X1 plus W2 X2 is greater than equal to theta. So this is a excitatory condition, and W1 X1 plus W2 X2 less than theta, that is inhibitory condition. So you can assume, you can first replace the values. So for first three cases, we will going to substitute in the first equation, and for the last case, we will going to substitute in the last equation, and then you just get the equation. So uh, so the first one will be what? W1 plus W2 greater than equal to theta, because 1 will going to substitute, x1 x2 is 1. Then the second equation will be what? The first part is what? 0 over here, x1 is 0, so this will become 0. X2 is 1, right? So W2 is okay, it's not written for this one, I think, because W2 is less than theta. It's not written properly. Let me check if there is any, or yeah, this here it's there. Okay, so you can assume anything, right? This equation up to you. So according to that, the value will come. So in this particular part, I've taken what? W1 x1 plus W2 x2 greater than theta. So it's okay. So the next will be what? W1 x1 plus W2 x2 less than equal to theta. So this will be inhibitory condition. So for the first three cases, we are getting excitatory, and for the last one, we are getting inhibition. And then you can first form the all the four equations. So this will be, first equation will be W1 plus W2 greater than theta. W2 is greater than theta because x1 is 0, so only 1 we will get, right? So this will become W2 greater than theta. Then the third pair is what? 1 0. Let's substitute 1 0 1. So this will become W, and this part will be 0. So 1 is greater than theta. So W1 is greater than theta, right? And the last one is 0 0 is 0, right? So we will going to substitute in this, and this is the inhibitory condition. So we'll substitute in the second equation. So 0 0, that means 0 is less than equal to theta. So we got this four equation. Let's try to assume certain value. Let's say W1 is equal to W2 equal to 1 and theta equal to 0. Let's try to verify whether all the four conditions are getting validated. So if we will take W1 W2 as 1, so 1 plus 1 2, and theta is what? 0. So 2 is greater than 0, yes, first is getting validated. W2 as 1 is greater than theta, theta is 0, yes. W1 1 is greater than 0, right? Then 0 is less than equal to theta, so theta is 1 and this is 0, so 1 is greater than 0. This is also getting validated. So that means whatever weights we have selected and the theta we have selected, that is proper. And then finally we can make, we can write this particular logic: output is equal to 1 or 0 if theta is greater than 0, or theta is less than equal to 0, right? Based on whatever firing and inhibitory condition we have taken. So both the methods are good. It's up to you which method you are selecting. So if you see here, I have also demonstrated with this particular part, like W1 x1 plus W2 x2 greater than equal to theta, then less than theta. Then how we can choose. So here some other values we got, right? So it's up to you. There can be multiple set of values, and it's not necessary that everybody's answer will going to match. Only thing, the four condition you need to satisfy. So is there any doubt in this particular problem?
No, sir.
Okay. So what we will do, we will end this particular session till here, okay? And then from the next lecture, we will going to solve the XOR problem and all. So for today, it's enough. And after this, I'll have to attend one meeting also, which is very important. So let's end this particular session over here. And if you have any doubt, you can ask me.